a look at using graphs and tables of functions, and we're specifically going to look at applying what we learned about domain and range to those graphs and those tables of the functions. So before we get in, let's do a little bit of terminology. Today we're going to take a look at two different types of graphs, a continuous graph and a discrete graph. Continuous simply is a graph that can be drawn by putting your pencil down on the paper and drawing it from beginning to end. There are no unbroken pieces of that graph. A discrete graph, on the other hand, is going to appear broken. It's going to be either line segments or just a random bunch of discrete points plotted on the graph. So you can see we have two examples down here. For example, 1. This first one under letter A is going to be a discrete graph. It appears broken or just scattered points along that graph. I would have to pick up my pencil in order to plot that. Now we're also asked to give the domain and the range. Well, here our domain using set builder notation are going to be all of our x values here. So you can see that we start off here at -3, -2, -1. So I'm going to list those, separated by commas because these are just integer values. Then I have 0, 3, and 4. All right, there's my domain, which remember are my x values. Next up I have my range, which are my y values. And again, I'm just going to take the y coordinates here. So it looks like -1 is used twice, 0, +1, +2, and +3. So I only need to list, -1 once. I'm going to list this in reverse order there. And then we're going to go to +1, +2, and +3. And there is my range for that discrete function. Well, over here in letter B is going to be a continuous function. You can see that I could graph this squiggly line, which you guys are going to come to find out is known as the sine or the cosine curve later on in the year. And I can do that without lifting off my pencil off the paper. So this is going to be a continuous function. And again, I'm going to list my domain and my range. So my domain, if we were to think about flattening this curve on the x-axis, it looks like all of my x values would be covered. So I would say my domain here is a set of all real numbers, and my range are my y values. If I were to flatten this like an accordion onto the y-axis, it looks like it'd go from this +2 to 0. So my minimum value would be 0, less than or equal to y, which is less than or equal to 2, the maximum value. All right, let's move into example 2. Now we have an example of a continuous graph with a real-life application. So let's make sure we read through that problem and understand the context of it. We got Maria. She is going to travel a particular distance during a 7-hour trip to the museum. After the museum, she met a friend for dinner before returning back home. So you can see here I have my two variables, x, which goes along, time, which goes along the x-axis, and distance from home, which goes along my y. And I'm asked to determine here which variable is a function of the other. So remember, it's always our y that depends on our x. Our y is a function of the x. So here we're going to say that distance is a function of time. In other words, the distance she is away from home depends on the time of her trip. State the domain and the range of the function using set builder notation. So let's start off with our domain, which are our x values. And again, if we were to flatten this curve along that x-axis, you would see that it would contain everything between 0 and 7. And because it's continuous, we can write that as an interval just like this. All my x's between 0 and 7. All right, next up is our range. Our range is our y values. If we were to flatten this curve along the y-axis, you could see that I'm going to cover everything between 0 all the way up to 100 miles. So all my y values, and again, because this is a continuous function, I can write that interval just like this. These are all my y's that are greater than or equal to 0, but less than or equal to 100. All right, now we're going to get into interpreting and reading some of our inputs and our outputs from a graph. It says to estimate Maria's distance from home after 3.5 hours. Write your answer using f of x notation. So that's function notation. So we're going to say the distance based on the time, here's our function notation, at 3.5 hours. So in other words, our distance away from home at 3.5 hours. So our input is 3.5. In other words, our x value is 3.5. So I'm going to go over on the x-axis to where 3.5 is, and I'm going to come up to where the graph is, and that's the result when our argument is 3.5. So I'm going to just read that across here to the y-axis. It looks like that's somewhere between 75 and 100. So we're just going to guess that is approximately 85 miles. It's important to use that unit of measurement on there as well. All right, how long was Maria at the museum? Explain how you know. Well, remember, she took a trip to the museum. Looks like here, this flat line indicates that she's not traveling further away from home at this time. So it looks like from an hour and a half here to maybe to 3 hours, Maria is at the museum. So how long is Maria at the museum? From between the hours of 3. Let's try this again. We're going to subtract 3 minus 1.5, and that's going to give us another 1.5. So she was at the museum for 1.5 hours. And again, what we're doing there is we're just counting this horizontal distance here between 1.5 hours and 3 hours. All right, how long did it take Maria to make her return trip home? So after the museum, she went to dinner with a friend. She stayed at dinner. That flat line there indicates she's not traveling away from home. And then from dinner, she drove all the way home. And it looks like it took her between 5 and 7 there. So that is a total of 2 hours. All right. Next, let's take a look at our next example here. Robert Waldo is the tallest person in medical history who has a height that has been recorded. The table here gives his height h at various ages a, where h is a function of a. Okay, so your height is a function of your age. In other words, your height depends on your age. So your age is your x value here, and your height is your y value. All right, we want to find the domain of the range. It's defined by this table. So I think you guys are getting pretty good at this. Our domain are our x values here. And these are discrete values, okay? So we're going to list them as such. They are not a range of continuous or real numbers. They're just going to be these discrete values, these integer values. All right, our range then are going to be the outputs here, 1.9, 2.0, 2.4, 2.5, and 2.7. Now remember, this is measured in meters, so multiply each of these by a little bit over 3, and you're going to find out how many feet Robert Waldo is. And you can see here, I'm pictured here next to Robert, and you can see I'm pretty tall myself. So next up, it says to explain this notation, this f of 16. What does f of 16 represent? What does it mean in the context of the problem? So our argument, or our input, or our x value here is 16. So I'm going to go to where x is 16. F of 16 is equal to 2.4. Now, in the context of the problem, this means that Robert was 2.4 meters tall. That's a point in there, 2.4 meters tall at age 16. So when he was 16 years old, that's how old you guys are. So are you 2.4 meters tall? Probably not. You're probably closer to my height. All right, so what value of a produces f of a is equal to 2.7. So keep in mind, f of a is just a fancy way of saying your height. In other words, we want to know the a value, the age, or the input, when your height was 2.7. So what a gives us 2.7? So we're going to come here and look at the heights. 2.7 is found when a was 22. So that means when he was 22 years old, he was 2.7 meters tall. All right, one last example for today, and this involves our graphing calculator. So take a second to grab your graphing calculator. And I'm going to pull mine up as well. All right. So here's our graphing calculator, and we're ready to get going. When anthropologists find a leg bone, also known as a femur, they can estimate how tall that person was using this equation. H of x is equal to 2.59x plus 66.4, where x is the length of the femur in centimeters and h is the height. We're going to enter this function into our graphing calculator, also called your CAS. Your book is going to refer to that sometimes. Just an abbreviation for computer algebraic system. All right. Next, we're going to set up a table that starts at 30 and goes up by 2. So let's start by entering our equation. We're going to go to our y equals, and we'll put in our 2.59x. See if you can follow my keystrokes there, if you can't remember from the other day where the x was, plus 66.4. All right. There is our y equation there. And if we want to take a look at the graph, we could press graph, but we're not really interested in the graph. We're interested in the table here. So we're going to hit second function, table. And my table starts at 0. Yours might as well. But remember, we want our table to start here at 30. So we can actually change that by pressing second function, window. This should take us to the table setup. The first line asks us where we'd like our table to start. Let's start our table at 30, and let's arrow down. The next line, this little triangle TBL, tells us how we want our steps to go up by. Well, we want our steps to go up by 2, so we're going to change that to 2. Now, when we press second function, graph, that will take us to our table, and you'll notice that it starts at 30 and goes up in increments of 2. So we can copy down here into our table 30, 144.1, 32, 149.28, 34, 36, 38, 40, so on and so forth. Take a second to do that, and then we're going to answer part B. All right, part B says estimate the length of the femur when the skeleton found measures 162 centimeters tall. So